What's up, guys? This is Jahangir from Emporium, and today we're going to be talking about projectile motion. So projectile motion is a little bit more different from free fall, because in free fall our object was moving only in the y-axis with the implement of gravity. So when we dropped a ball from, say, a roof or anything that had a lot of height, we would be in free fall because that ball would only be in the y-axis when we dropped it. Now projectile motion is a little bit more different because we're also going to include the x-axis as well, the x-coordinates. Now, with projectile motion, we have to account for our initial velocity and gravity, because initial velocity and gravity are going to be two components that really determine our trajectory of an object. So projectile motion is, some examples are like throwing a football. So when you throw a football, let's just say this is our football, it's going to make a sort of parabola type of curve, you could say. So when you throw a football, it'll reach its maximum point, maybe somewhere over here, and fall down due to gravity. So that is the conceptual side of projectile motion. There's other things that we need to talk about as well, such as acceleration. Now, acceleration in the x-axis is going to be 0 in projectile motion. The reason why is because in our x-axis, when we throw a football, when we throw a ball, when we're in projectile motion, our velocity is going to be constant. So I could say Vx is constant. So we have constant. And that is in projectile motion, where our velocity in the x-axis is going to be constant, and that's why our acceleration is 0. Now, just like free fall, our acceleration in the y-axis is going to equal gravity, and since gravity is in the downward direction, we're going to put a negative right there. So our acceleration is going to be gravity. So this is exactly how we can break down projectile motion. It is in the x-axis, we have horizontal motion, which we have constant velocity, while with acceleration, we have a changing velocity and we have an acceleration due to gravity. So just remember that in projectile motion, our acceleration is going to be constant on the x-axis, our velocity is going to be constant, and our acceleration on the y-axis is just going to be gravity, because when we throw a football, when we throw a ball, the only force that's acting upon that ball, and the reason why it actually falls down, is gravity, given that we're saying that this is a perfect model and we're neglecting air resistance. Because many of these kinematic problems that we go through, we are going to neglect air resistance as one of the forces, and we're just going to say that there's gravity acting upon that object, just to make things a lot more simpler. So how can we visualize projectile motion yet again? So we use our football example, and we'll actually put y and x coordinates. So we'll put our x and y sort of graph over here. So this is going to be y, this is going to be x. So we're saying that we're throwing a football. So a football, the trajectory, if we throw it, is going to look like a parabola. So we could do something like this maybe, and this would represent our football. Now, when we're starting off, and let me actually change my color to say that it's red. So when we're starting off over here, let's just say this is where we're throwing the football. This is where we're actually kicking a soccer ball. So either way you want to think of it, we'll just go with the example of kicking a soccer ball, because you kick a soccer ball from the ground. So over here, we're going to have our velocity initial in the y-axis, over here velocity initial in the x-axis, and overall our velocity is going to be this curved line, straight line over here. So one thing you'll notice is that our velocity in the x-axis and velocity in the y-axis will stay perpendicular. So our velocity over here will follow that curve, and we'll get to a point over here where we reach our maximum point. Now our velocity will be 0 over here, because as you can remember from free fall and talking about projectile motion as well, every time we reach our maximum point of that trajectory of that object, our velocity is going to be 0. So reach that point over here, and then we sort of change directions over here. So this is still going to be Vx, Vy, and our velocity is now going to be over here. So as you can see, we switched from a positive velocity to a negative velocity. And this is what happens when, as you can remember from our past videos, when we go to that maximum height, we change directions and we end up with, in this scenario, a negative velocity. And this continues to go down, and as we can remember, our acceleration in the y-axis is going to be gravity. So during this whole time, our velocity in the x-axis is going to stay constant. The only thing, and we're assuming that this is a perfect model, no air resistance. The only force that's acting upon this soccer ball when we kick it is gravity, and this is what creates that parabola. This is what creates that projectile motion. Now, one of the biggest things to realize is that horizontal motion is independent of vertical motion, meaning that our motion in the x-axis, which is constant velocity, does not depend on gravity because that constant velocity will stay the same. So both horizontal motion and vertical motion are independent, which when we're solving these questions, we have to treat them as independent. And that's why we use different equations and we solve them separately because these are two independent motions. So before we get into those practice problems, we really have to write down our equations we're going to use for horizontal and vertical motion. So if you remember from the big three, we're just going to be using some of those. But specifically, if we look at horizontal motion, and I'll just model it by x motion. Horizontal motion, our acceleration is going to be 0. So there's no point in using one of the big three equations that has acceleration because we know that acceleration is going to be 0 because velocity is constant. So the equations we're going to use is our velocity initial is going to be velocity final or just the velocity entirely because we're saying that velocity is constant throughout this projectile motion. So whatever velocity we started off in the x-axis, that's what we're going to end off with. Now to find distance, that would just be x, and we have our initial position plus initial velocity times time. And this is if we wanted to find the distance that has been traveled from the x-axis from either point A to point B. Once we kick that ball, we're pretty much asking how far did that ball go. Now let's look at our vertical motion and modeling it by y motion. So vertical motion, we have acceleration. We know that, and that acceleration is due to gravity. So some of the equations we're going to use is our velocity equals velocity initial minus gravity times time if we wanted to find our vertical velocity. And we can also use our position in the y-axis plus velocity initial in the y-axis minus 1/2 gravity times squared if we wanted to find how high that ball was kicked, how high that soccer ball was kicked, what the maximum height is, anything like that. And this might be a review for some of you guys, but when we're looking at these vectors over here and we have velocity in the x-axis, velocity in the y-axis, the velocity in the y-axis is going to equal velocity initial sine theta because this is our velocity over here, velocity initial, you could say, initial velocity cosine theta. And if we wanted to find the degree or the direction in which we were sort of moving in this velocity, if we wanted to find this theta over here, our theta would equal tangent inverse of velocity y or velocity x. So now let's look at a practice problem in projectile motion. And this one's actually pretty simple. It says a baseball is hit with an initial speed of 37 meters per second at 53.1 degrees. The first part asks us to find the ball's position as well as the magnitude and direction of its velocity when t equals 2 seconds. So obviously we need to use one of our equations for our x motion, and our second part is find the time when the ball reaches the highest point and find the height at that point. So that's y motion, and the horizontal range obviously is going to be x motion. So to go through this practice problem, let's see what we're given. So we know our initial velocity is going to be 37 meters per second, and we have our theta, which equals 53.1. So automatically, one of the things we could do is, first off, let's actually write how we can visualize this practice problem. And if you can, I highly encourage you guys to pause this video and see if you could solve all of these parts. So with this type of motion, we're going to have our vectors that we had before with our velocity in the x, which we know is going to be initial velocity cosine theta, and I'll just write our velocity over here, and our theta is going to be over here, which is 53.1, and over here our velocity initial in the y-axis is going to be velocity initial sine theta. So from here, all we have to do is just plug in our numbers. So this is going to be 37 meters per second, and this is going to be sine 53.1. And for this one, I just won't put the units. But remember, you do have to put your units when you find your final problem. I'm pretty sure you have to do that according to your professor. So over here, our velocity is same thing, 37, and I just won't put units for this one, cosine 53.1. So if we do the math, we know that our velocity in the y-axis is going to be 29.6 meters per second, and on our x-axis, it's going to be 22.2 meters per second. Okay, so the reason why we had to find our velocity in the x-axis and velocity in the y-axis is because if you remember from our conceptual understandings, it is that we treat vertical and horizontal motion independently. So to find our maximum height, to find the horizontal range, we have to find the velocities in the y-axis and x-axis in order to solve those, which we just found. So over here, we could write in just short terms that our velocity in the y direction is going to be 29.6 meters per second, and our velocity in the x direction is going to be 22.2 meters per second. So that's pretty much all we need, because we know that initial velocity is going to be equal to the velocity throughout the entire projectile motion. So this is all the information we need to extract. And now let's actually go through each of the parts of the question. So part A is asking us the ball's position and magnitude and direction of the velocity when time equals 2 seconds. So if we look back at some of our equations, we know that this is for horizontal motion specifically, because we're looking at horizontal motion. So our x is going to be initial position plus initial velocity times time. Now, one of the assumptions you can make is that our position is going to be 0. So we have everything else, and all we have to do is find this x over here. So this is going to be 22.2 meters per second, and this is times 2 seconds, which is going to equal 44.4 meters. And that is the ball's position at time 2 seconds. Now, to find the magnitude and direction of the velocity as time equals 2 seconds, that's when we have to bring our y motion. So now we have to bring in our equations for our vertical motion, which is going to be y equals initial plus velocity initial times time minus 1/2 gravity times squared. The reason why we need to do this is because we talked about how our trajectory, which is pretty much the magnitude direction of our object, is going to be dependent on initial velocity as well as gravity, because gravity is pretty much the force that is applied in order to create that parabola in order for our projectile motion to occur. So all we have to do, yet again, is just plug in our numbers, but this is for y motion, so we're looking at our velocity in the y-axis, so this is going to be 29.6 meters per second, and just like when we were talking about position initial for the x-axis, position initial for the y-axis, we can assume that that is 0, so this is going to be times 2 seconds, and this is going to be 1 minus 9.8 meters per second squared, and this is going to be times 2 squared, and when you do all the math there, you're going to get 39.6 meters. So now we found our position, or our height at which we're at when our time equals 2 seconds. So now let's find our velocity at 2 seconds, because our y-axis in vertical motion, our initial velocity is not going to equal the velocity at any other time like 2 seconds. So that's why we have to use our equation. Velocity in the y-axis equals our initial velocity minus gravity times time. Now over here, we were able to assume that our velocity initial equals velocity throughout the entire time for the horizontal motion, but for this vertical motion over here, we have to understand that acceleration is not 0. Velocity is changing, so this initial velocity is not going to equal the velocity throughout the entire projectile motion. So to find our velocity at time equals 2 seconds, that is when we have to use this equation, and we just plug in our numbers. So our initial velocity in the y-axis is 29.6 meters per second, and over here I think I forgot to put the initial velocity, but that's an error on myself. This is supposed to be the initial velocity over here, so this is going to be minus 9.8 meters per second squared, and we're looking at time 2 seconds. And when you pretty much do the math, you're going to get 10.0 meters per second squared. And that is our velocity at time equals 2 seconds. So now that we know that, remember that this is our velocity in the y-axis as time equals 2 seconds. This is not our velocity when we are in time equals 2 seconds. This is our velocity for the y-axis. So now we have to use another equation, which is going to be velocity equals, and this is pretty much the Pythagorean theorem, because if we look back at this equation over here, we're just saying that if we look at our x and y-axis and we use Pythagorean theorem for that, our hypotenuse is going to be our velocity. So over here, we're just using the Pythagorean theorem, but just simplifying it down. So this is going to be our velocity in the x-axis squared plus velocity in the y-axis squared. And when we plug in our numbers, we're going to get something like this. So it's going to be 22.2 meters per second. And if we remember, our velocity in the horizontal direction will stay constant. So it's just going to stay as 22.2 meters per second. But over here at time equals 2 seconds, that's when we have 10 meters per second squared. So this is going to be plus 10 meters per second squared. And we're going to square this as well. And our total velocity, the velocity at time equals 2 seconds, is going to be 24.3 meters per second. Now to find our direction, it's going to be our theta, which equals tangent inverse of our velocity in the y-axis over velocity in the x-axis. Now I'm just going to move this over here, and what we're going to get is tangent inverse of 10 meters per second over 22.2 meters per second, and what we get is 24.2 degrees as our direction. So hopefully that made sense for part A, because all we have to do is use our equations towards pretty much our benefit. Now let's move on to part B. So in part B, we really have to understand the conceptual side of physics. And remember, if we're at our maximum height, because we're wanting to pretty much know the time when the ball reaches its maximum height and at what height that actually is. So when we're in our maximum height, our velocity in the y direction is going to equal 0. So if we know that, we can look back at our past equation looking at velocity initial plus gravity times time. If we know that this velocity is going to equal 0, and we know our initial velocity for the y-axis is going to be 29.6 meters per second, then this is going to be plus negative 9.8 meters per second squared. Remember, we're in gravity. Gravity is going to be on the downward motion, so it's negative. You could also say, and look at this equation, just say that this is going to be negative g. But you can also go about this way. Just remember that gravity is going to be negative because it is in the opposing direction, and our time, which is what we're wanting to find, is t over here. So all we have to do is basic algebra. So we move our 2.29.6. So this is going to be negative 29.6 meters per second equals negative 9.8 meters per second squared, and this is times time. And if we move this under, so I can just move over here and put this under over here. If we divide 29.6 meters per second, that's negative 29 meters per second, divide that by negative 9.8 meters per second. Let me move my time over here. Then our time is going to equal 3.02 seconds. And at 3.02 seconds, that's when we reach our maximum height. Now we have to figure out, well, what is our maximum height? Remember, height is in our y-axis, so all we really have to do is use our equation, one of the big three equations. So we know our initial velocity, or initial position, our initial height, you could say, is going to be 0. So we can disregard that, and we have 1/2 gt squared. So this is going to end up being 29.6 meters per second. This is times 3.02 seconds. This is minus 1/2 9.8 meters per second squared. This is times 3.02 seconds. And when you do the math yet again, you are going to get y equals 44.7 meters. And 44.7 meters is the maximum height. And at 3.02 seconds, that's when we meet our maximum height. So now let's look at problem C. And this is another problem where we have to apply our understanding of conceptual physics. So if we think about horizontal range, we know that from our start and even our end position, our position in the y-axis is going to equal 0. So since we know that, all we have to do is find the time in which our position is going to equal 0, and using that time, we can find our horizontal range. So it's going to be using one of our big three equations over here. So this is, and I'm just writing off our initial position in the y-axis because we're assuming that that's 0. So this is going to be minus 1/2 gt squared. And this is, in our y over here, we could just label this as being 0. So this is going to be 29.6 meters per second, and we don't know our time, which is what we're trying to find, minus 1/2 9.8 meters per second squared, and we don't know our time over here either. So this is a quadratic formula question, and to solve these questions, you could go the old-fashioned way and try to solve it using the quadratic formula, or you could program the quadratic formula into your TI-84 and it'll pretty much solve that for you. So there's a link down below showing you a YouTube video on how to do that. And once you do that, you're going to find that your time is going to equal 0 and your time is going to equal 6.04 seconds. Now, the reason why we're getting time 0 and time 6.04 seconds over here is because we need to remember that this is a parabola. Projectile motion is a parabola, and it's pretty much looking like this. So we have our roots, which is going to be time equals 0, time equals 6.04 seconds. So we really need to rely on this 6.04 seconds as our end position, because although we have two roots that we can use, we're using this time equals 6.04 seconds. And you can also use common sense, because if you think about it, we're not going to meet our final position when throwing a ball at 0 seconds. So now that we know our time, we could just use our equation, velocity initial on the x-axis times time, which is going to equal 22.2 meters per second, and this is times 6.04 seconds, and what we get is 134 meters. So hopefully this video helped you guys understand projectile motion and how to go through those practice problems. Leave a comment below if you have any questions about any of the problems we went through. And as always, a Pomodoro day will make you a doctor someday. I'll see you guys in the next one.